Okay, so we're going to finish up this problem here by going through and continuing to do more row operations to simplify down the matrix. And it's kind of interesting because the more operations you do on the matrix at this level of the problem, the less work you have to do later on when it comes to solving for the solutions. So kind of a good idea to kind of simplify as we go. So for our second row, we're going to make it match the top row when it comes to that second entry. So we're going to multiply it by a -1 minus 2i. And that's going to be times row 2, put the result back into row 2. So when we multiply that out, we are going to end up with 1, 2 plus 4i and 3i, and then down here a 0. And then we're going to have a -2, and then we're going to have a minus 4i. And then we have to multiply off to the side the two complex numbers, 1 plus I times a -1 minus 2i. So when we multiply those together, we're going to have, first of all, a -1 as a leading term, then a -2i, and then a minus I, and then a minus 2i squared. So that's going to actually become a 3 from, actually it's a negative, actually, wait a minute. Yeah, so it's going to be a -3. Nope, actually, that's going to be, let's just do the work, -1 minus 3i minus 2i squared, so that's -1 minus 3i, and that's going to be then plus 2, so that's going to be 1 minus 3i. All right, so that's going to go in that spot. We're going to have, again, a 1 minus 3i. And, of course, it's a row of zeros down below. So now we'll add row 1 plus row 2 and put the result into row 1. All right, so in doing so, 1 plus 0 still stays a 1. When we add those numbers there, the -2 and the 2, and the 4i, the -4i, we do get that very important 0. And then when we add those together, the 3i plus the 1 minus 3i, we get just a 1 there. And then down here, we still have our 0, our -2 minus 4i, and our 1 minus 3i, and a row of zeros. We're almost to the point where we can start figuring out our vector, but it's a really good idea to turn that leading number there, that -1 minus 4i, into a real number to make our calculations easier. So we'll multiply by the conjugate again. This will be -2 plus 4i times row 2, put the result into row 2. So top row is still 1, 0, 1. That's still a 0. But now that -2 times that -2 makes a 4. The two middle terms cancel. And then we end up with a -16i squared, which is 16. 4 plus 16, that makes a 20. And then for the other part, we will multiply our 1 minus 3i times our -2 plus 4i. Multiplying that out gives us a -2 plus a 4i plus a 6 times I, and then we're going to have a minus 12i squared, which is plus 12. So that's going to make a 10 plus 10i. So in that spot goes 10 plus 10i, and we still have a row of zeros. One last thing to do is take 1/10 of row 2, put the result into row 2. So that's going to give us a matrix of 1, 0, 1, 0, 2, 1 plus I, and then a row of zeros. Now remember, this is still times that eigenvector v1, v2, v3 equaling 0, 0, 0. So the first equation tells us that 1v1 plus 1v3 is equal to 0. So v1 equals the opposite of v3. The second row is a little bit more complicated. It says that 2v2 plus the number 1 plus I times v3 is equal to 0. So 2v2 equals -1 minus I times v3. So that tells us that v2 is -1 minus I over 2 times v3. And that gives us our eigenvector, which is kind of ugly, but it's a negative v3 in the first spot, a -1 minus I over 2 times v3 in the second spot, and a v3 in the last spot. And if we pick v3 to be equal to the number 2, then we end up with a -2, a -1 minus I, and the 2 as our corresponding eigenvector. And again, that was from when lambda was equal to 2I. So we now have our one real eigenvector, and then we have our complex eigenvector corresponding to the eigenvalue 2I. So next part of the problem, we'll start putting all of this together.